Word break problem. Have you ever faced the word break problem in a tech interview? This is one of the most popular Pattern Mastery 100 LeetCode questions, appearing everywhere from Google to Facebook. More than 35% of candidates stumble here because it tests your ability to combine dynamic programming and hashing under pressure. Mastering word break is not just about solving one problem, it's about unlocking a core interview skill. So, let's break it down together and ensure you never trip over this one again. Let's break down the word break problem. We're given a string S and a list of words, word dict. The challenge is, can we split S into a sequence of dictionary words? For example, if S equals cat, sand, dog and word dict equals cats, dog, sand, and cat, can we build S using just these words, without reordering or skipping letters? We want a Boolean answer, yes or no. Now, let's assess the complexity. The brute force approach would check all possible splits, exponentially slow. But we can do better. If we use dynamic programming, we can store sub-problem results. For every index in S, we ask, can I split up to here using the dictionary? A hash set gives us O1 lookups for dictionary words. Edge cases, empty string, should return true. And if word dict is empty, we should return false. Next, let's structure our solution. We'll build a DP array, DP, where DPI is true if S, I, can be broken into dictionary words. Set DP0 equals true as the base case, empty string is always breakable. For each position I, check all possible partition points j before I. If dpj is true and sji is in word dict, set dpi equals true. Finally, return dplens. Let's try to implement it using solution 1. Time complexity is O(n) squared. Space complexity is O(n) plus m. This solution uses dynamic programming plus a set for fast word lookups. The core idea is to track which prefixes of the string can be successfully broken into dictionary words. We create a Boolean DP array where DP at I means the substring from the start up to index I can be segmented. We start with DP at 0 equals true because an empty prefix is always valid. Then, whenever we find a valid break at position I, we try extending from I to future positions j. If the substring from I to j is a dictionary word, we mark DP at j as true. At the end, DP at n tells us whether the full string can be segmented. First, we store the string length. Then we convert the word list into a set so checking if a word exists is quick. Then we build a DP array of booleans. DP at I represents whether the first I characters can be split into valid dictionary words. We set DP at 0 to true because the empty string is already successfully segmented by default. Next, we scan through the string looking for positions I where we already know the prefix up to I is valid. That DP check is important. It means we only try to branch out from places that are actually reachable. If a prefix cannot be segmented, there is no point trying to extend from it. From a valid start point I, we try every possible endpoint j ahead of it. For each slice from I to j, we check if it is a dictionary word. If it is, we mark DP at j as true. That means we have found a way to segment up to j. Over time, this builds a trail of reachable positions. Either we can reach the end, or we cannot. Finally, we return DP at n. DP at n represents whether the entire string from start to finish can be broken into dictionary words. If it is true, the segmentation is possible. If it is false, it is not. And that's how this algorithm works. It first sets up a DP array to track which prefixes are segmentable and a set for fast word checks. Then it expands from each valid breakpoint to mark new reachable positions until the end becomes reachable. Efficient, simple, and elegant. Test case check. Word break using dynamic programming. Let's test our function using this input. S equals LeetCode and word dict equals LeetCode. The string represents the full word we want to break apart, and the list contains the valid dictionary words we're allowed to form. Here's why the solution works. Our DP array DPI tells us whether the substring S0:I can be segmented using the dictionary. We start with DP0 equals true, meaning the empty prefix is always valid. Then, for every index I where a valid segmentation exists, we try expanding forward to every j greater than I. If the substring Sij is a dictionary word, we mark dpj equals true. And that's exactly what our program outputs, true. The result matches the expected output, confirming that the DP logic is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether the entire string can be segmented into valid dictionary words, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is O(n) squared. Space complexity is O(n) plus m. This solution uses recursion with memoization. That means we try all possible word splits, but we remember results so we do not repeat work. We start from an index in the string and ask a simple question. Can I break the rest of the string into valid dictionary words? From that start point, we try every possible next word by moving an end pointer forward. If we find a word in the dictionary, we recursively check if the remaining suffix can also be broken. Memoization stores whether a certain start index is breakable or not. So if we ever come back to the same start, we instantly reuse the answer instead of rechecking all splits again. First, we convert the dictionary into a set so word lookups are fast. Then we create a memo map. The key is a starting index in the string. The value is whether the substring starting there can be successfully segmented. This memo is what keeps recursion from exploding into repeated work. Now we define can break with the start index. Its job is simple. Starting from this index, can we split the remaining part of the string into dictionary words? This turns the big problem into smaller, repeatable subproblems. Here are the two quick exits. If start reaches the end of the string, that means we have successfully broken everything. So we return true. And if we have already solved this start index before, we return the stored answer immediately. That saves a huge amount of repeated searching. This is the exploration step. We move the endpointer forward to create every possible substring starting at start. If that substring is a valid dictionary word, we then recursively ask another question. If we jump to end, can the rest be broken too? The moment we find a path that works, we store true in the memo for this start, and we return immediately. We do that because we only need one valid segmentation to succeed. If we try every possible split and none of them work, then this start position is not breakable. We store false in the memo so we never waste time rechecking it again. And we return false. Finally, we start the search from index 0. That means we are trying to break the entire string from the beginning. And we return the result. And that's how this algorithm works. It first sets up a set for quick dictionary checks and a memo map keyed by start index, then it recursively tries every possible next word and uses memoization to reuse results and avoid repeating failed paths. Efficient, simple, and elegant. Test case check. Word break using DFS plus memoization. Let's test our function using this input. S equals apple pen apple and word dict equals apple, pen. This string represents the full sentence we want to break apart, and the dictionary contains the valid words we're allowed to use. Here's why the solution works. We explore the string from left to right using recursion. At each position, we try every possible substring as start end. If that substring is a valid dictionary word, we recursively check whether the rest of the string can also be segmented. And that's exactly what our program outputs, true. This confirms that our memoized DFS logic correctly identifies valid splits and handles repeated patterns efficiently. Wrap up. So, our implementation is correct. The algorithm successfully determines whether the string can be segmented using recursive search with memoization, efficient, accurate, and reliable. Word break problem. Let's do a recap. Ever hit the word break problem in an interview? It's one of those dynamic programming classics that separates good candidates from great ones. This challenge isn't just about splitting a string, it's about recognizing patterns, using efficient lookups, and proving you can think dynamically under pressure. Breakdown recap. We began with the goal. Given a string and a dictionary of valid words, can we split the string into a sequence of dictionary words without reordering or skipping any letters? Essentially, we're checking if the entire string can be built piece by piece using only the given words. Assess recap. We compared brute force and dynamic programming approaches. Brute force tries every possible split, exponential and inefficient. The DP method, on the other hand, reuses previously computed results to make smarter decisions, while hashing gives us instant dictionary lookups. Together, they form an elegant O(n)² solution. Structure recap. The plan was simple but powerful. We used a DP array where each index represents whether the substring up to that point can be segmented into valid words. Starting from an empty base case, we built our solution step by step, checking all possible word boundaries along the way. Implement recap. We implemented the DP logic with efficient hashing and ran it on LeetCode. The code executed smoothly without any errors, correctly determining whether the string can be segmented. Check recap. We verified the logic by testing with sample inputs and confirmed that the output matched expectations. The algorithm passed all test cases successfully, confirming the DP table and logic worked exactly as intended. Closing insight. The big takeaway? Mastering word break teaches you how to merge dynamic programming and hashing, two of the most important tools in problem solving. Once you see how they work together, you'll not only solve this problem with confidence but also spot the same pattern in dozens of future challenges.